In the M5-Final, I built a machine learning model to predict low default risk using the home credit dataset. The objective is to estimate the probability that a borrower will default on their loan. I started the project by exploring the dataset using exploratory data analysis. The dataset contains several thousand loan applications and more than 100 variables describing applicants' financial history, demographic information, and credit-related attributions. One important observation from the EDA stage is that dataset is highly imbalanced. Only a small proportion of applications actually default on their loan, while the majority repay successfully. Because of this imbalance, accuracy alone is not a reliable matrix, since a model could achieve high accuracy simply by predicting the majority class. Therefore, during the rest of the project, I focused more on metrics such as record F1 score and ROCAUC. During the EAD stage, I also explained the missing value and the feature distribution. Several variables contain missing data. Before building model, I implemented a processing pipeline. First, I removed the consumer ID column because it does not contain predictive information. Then I split the dataset into train and validation and testing data so that the model could be evaluated on unseen data during the development. Next, I handled the missing values by inputting numerical variable with the median and the categorical variable with the most frequent value. After that, categorical variable were converted to numerical format using one-hot encoding. Since most machine learning cannot directly process categorical feature. Finally, I standardized the numerical variable so that features will have consistent scales. All these steps were implemented in a pipeline to ensure that same transformations are applied consistently during the training and prediction. After completing procession, I compared several machine learning models. These include logistic regression, random forest, gradient boosting, XGBoost, support vector machine, k nearest neighbors, and neural network. Each model has trained using the simple processing pipeline and evaluates on the validation dataset using metrics such as accuracy, precision, record F1 score, and ROCAUC. When comparing the results, I noticed that some tree-based models achieved very high accuracy but extremely low record. Since identifying high-risk borrowers is critical in credit risk prediction, record becomes a particularly important metric. Based on comparison results, logistic regression achieves the best balance between record F1 score and interpretability. So I select logistic regression as the final model. After selecting the model, I evaluate its performance in more details. I computed standard classification metrics including accuracy, precision, record F1 score, and ROCAUC. I also used a confusion matrix to better understand how the model makes predictions. The confusion matrix shows the number of true positive, true negative, false positive, and false negative. In the context of credit risk prediction, false negative are particularly costly because they represent borrowers who will default but are predicted to repay, which may lead to financial loss for lenders. False positive represent reliable borrowers who are incorrectly classified as high risk and may be denied credit. Understanding this trade-off helps explain how the model performs in real financial context. To ensure model's performance is stable, I also conduct 5-fold cross-validation on training data. Cross-validation evaluate the model across multiple data splits and pros a more reliable estimate performance. Another important aspect of the project is model interpretability. Since the model is used for credit risk prediction, it's important to understand why model makes certain decisions. I first examined the logistic regression coefficient to understand overall influence of features. To obtain more detailed explanation, I used SHOP values. The SHOP summary plot shows features such as X source 2, X source 3, and the AMT goods pricing. They have strong impacts on default prediction. In addition, the SHOP waterfall plot provides local explanatory for individual prediction. For example, X source 3 and AMT goods pricing increase the predicted default risk, while AMT annuity decrease the risk of specific applicants. This explanatory improves model transparency and support responsibility decision making. In addition to interpretability, I also evaluate the model from response AI perspective by analyzing fairness. Credit risk model may unintentionally induce bias if certain demographic groups are treated differently by model. To investigate this, I compare both actual default rates and the predicted default rates across gender group. I also calculate fairness-related metrics such as predicted positive rates, true positive rates, and the false positive rates for each group. These results show that while there are slight differences between groups, the model predictions generally follow the same pattern as the actual data distribution. This suggests that the model does not introduce a strong additional bias beyond the pattern already present in the dataset. However, fairness will be monitored continuously when deploying models in real-world systems. For the ethical perspective, credit scoring model have significantly social implication. Incorrect prediction can affect individuals' access to financial service. A false positive may incorrectly classify a reliable borrower as high risk and deny them access to credit, while a false negative may allow a high-risk borrower to receive credit, potentially cause financial loss for lenders. Because of this consequence, transparency, interpretability, and fairness are important consideration in financial machine learning applications. After validating model, I applied the final logistic regression model to unseen the test data set. Since the test data set does not contain the target variable, evaluation matrix cannot be calculated. Finally, before deploying such a model in practice, several production considerations must be addressed. The model should be continuously monitored for data drafts and performance degradation. Fairness metrics should also be periodically evaluated to ensure the model does not introduce unitant bias. In addition, human oversight should remain part of decision-making process, particularly for high-risk cases. In conclusion, the project developed a lower default prediction model using logistic regression and combined the predictive model with responsible AI practice such as interpretability and fairness analysis by integrating model performance, transparency, and ethical consideration. The project demonstrates how machine learning can support more responsibility and trustworthy financial decision system. Thank you.